Welcome to EIGRP, the Enhanced Interior Gateway Routing Protocol. We're going to hit the concepts of EIGRP first and take a look at what makes EIGRP tick. Now, we're first going to start off with why we choose to use EIGRP. And I'm just grinning as I'm looking at the concepts because they're so simple. Except for the metric. And we'll talk about the metric in a little bit. But I was debating when I put this whole series together whether to start off with OSPF, the brutal routing protocol, or EIGRP. And I thought we've got to start with EIGRP just so you can see how user-friendly EIGRP is before you see how unuser-friendly OSPF is. So we're going to take a look at those concepts, why we choose to use it, some of the tables and terms EIGRP uses, the neighborhood, meaning how neighbor relationships are formed in the EIGRP world, and then we'll look at the one difficult thing of EIGRP, which is the metric. Now you may have noticed that BSCI is all about routing protocols, one right after the other. We're going to talk about what they are, how to configure them, the advanced features, and so on. And when we look at each routing protocol, what I want to do is focus in on why would you choose this one? Every single one has its own unique niche market. So why would I choose EIGRP, the very first one we're going to look at? Well, this is an ordered list on what I would perceive to be the best benefit that you'll get, all the way down to the least, but they're all benefits. So the number one benefit you'll get from using EIGRP is the fact that this is the only routing protocol still in existence that supports backup routes. Meaning no other routing protocol has this. All other routing protocols find the best route to get to a network and then throw all the rest away. The one best goes in the routing table, the rest just get ignored. So what that means is for the other routing protocols, if they ever lose their best route, like a link fails, they have to scramble. Like RIP starts sending broadcasts saying, help, somebody help me, give me another route. OSPF has to look back at its topology database and, try and figure out, runs the SPF algorithm, which takes time and so on. EIGRP is the only one that will maintain something known as a topology table of backup routes. So if the primary fails, EIGRP doesn't have to figure out anything. It just looks at its backup route and goes, oh, well, here's one, and throws it into the routing table, making it one of the fastest to converge routing protocols that's out there. Now, you can also see right after that I have dual. It sounds like Star Wars, but at the same time, dual is the algorithm that EIGRP uses to find all these routes and the backups routes. Just like we have OSPF, and it uses something known as the SPF algorithm, the shortest path first. Dual is the diffusing update algorithm. The AL is one word, it's just algorithm, which is something that Cisco wrote to make this one of the most efficient protocols out there. It's very easy on your processor, it's very fast. Second benefit that I'll see that you get, and second in my list of rankings, is the simple configuration. That's what Cisco tried to do, is combine the best of distance vector and link state. You can see that all the way down there on number 5. But one of the features they took from distance vector was the ease of configuration. Even though EIGRP, it does just about everything OSPF does, one of the most advanced routing protocols in the world, you wouldn't know it from the configuration. You type in a few network commands and poof, you're running. It doesn't take much. Third, flexibility and summarization, meaning you can summarize anywhere you want in your network rather than having to have specific routers that can do summarization. It's wide open to you and your design. 4, unequal cost load balancing. No other current routing protocol does it. And I keep plugging in current routing protocol because some of you might remember a routing protocol called IGRP. It's not that old, but it was the predecessor or distance vector flavor of EIGRP that Cisco discontinued when iOS 12.3, some of the later versions came out, because nobody used it. Everybody went with EIGRP because it was so much better. So IGRP had a lot of these same features. It was just a scaled down version of EIGRP. But since it's gone, this is now the only routing protocol that does it. Unequal cost load balancing means it can take unequal links, for instance, a T1 and maybe a fractional T1 bandwidth connection, and unequally load distribute evenly across both of them. Now, when I say evenly, don't mix that up in the sense that it's not one packet here, one packet here. It will accurately load balance based on the bandwidth. So, for instance, if the fractional T1 is half the bandwidth of the full T1, it can say, well, I'll send 2 packets on the full T1 for every one that I send on the fractional. It gets very accurate with how it load balances. 5. Combines the best of distance vector and link state, meaning you get the ease of configuration along with all of the features of a typical link state routing protocol. Now, because of that, the official term for EIGRP is that it is a hybrid routing protocol. But if you were to, that's what Cisco calls it, it's a hybrid. But if you were to look deep into the trenches of EIGRP, you would find out it's officially categorized as an advanced distance vector routing protocol. And I guess I should expand a little on that, huh? It's because EIGRP does not have a full idea of what the entire network looks like a link state does. It has a partial view of the network, and we'll see more of that when we start exploring how it exchanges routes. The last benefit that's not supported by any other routing protocol, but is by EIGRP, is multiple network protocols. Now, I mentioned it's still a benefit, but nowadays it's people look at that and they're like, who cares? I don't run IPX, SPX, or Apple Talk anymore, which is the other 2 protocols it supports. So why would I need that? As I mentioned, it's a benefit. It's just the least of them. All right, now let's get a little deeper into the tables and terminology that makes EIGRP tick. An EIGRP router, the routing process, maintains 3 different tables: a neighbor table, a topology table, and a routing table. Now we'll look at the neighbor forming process in just a moment, but all of these routers will form neighbors. So router 1 will say, hello neighbor, router 2, router 4, you are my neighbor, and router 3 is a neighbor. Now a neighbor is just a directly connected router. These routers will exchange their routing tables with each other, meaning router 3 will tell router 1 about all of its best routes, all of the stuff that's in its routing table. Router 4 will do the same, and so will router 2. Now, I want to make this distinction right here, because when we look at OSPF, which is a pure link state routing protocol, you'll find out that the routers will exchange something known as the OSPF database. Some people call it the SPF database. It is a roadmap of everything that's available in the router's area. So it's kind of, think of it like a map. You look at a map, everybody's got the same map that they're working from, and they all find the best ways around the network. This is one of the reasons EIGRP didn't make the cut, if you will, into the link state world, is because all of the routers don't have a roadmap. They don't all have the complete area database of everything that's available. They just have the best routes from each of their neighbors. So the neighbors will all send their best routes to each other, and the routers will put those into its topology table. So router 1, for instance, will receive a route to the 10.1.1 network over here, 10.1.2, 10.1.2 from router 3 and router 4. All those routes go into the topology table. It does its little dual algorithm to figure out the best ways around, and then finally puts the best into its routing table. And the routing table will be what it uses to get around the network, and it will also be what the router advertises to upstream routers. So let's say we've got router 5 sitting upstream from router 1, 2, 3, and 4. When router 1 talks to router 5, if one of these routes were the best, meaning router 1 said, hey, router 3 is the best route because that's a T1 line, and this is a 2400 baud modem over here, so I'm going to pick this one, and it chooses that one. That's the only one it's going to tell router 5 about. Router 5 won't know about this link right over here, which is one of the major reasons that this is considered an advanced distance vector routing protocol. If this were a link state routing protocol like OSPF is, router 5 would know about that link, even though it's not going to use it, even though it's not directly connected, it would still be in its database. So 3 tables, and now a whole host of terms. And understanding the terms is half the battle when you get to EIGRP. The first 2 describe how far away a route is. You see feasible distance and advertised distance. Now, feasible distance is how far it is away from you as a router. So if I were router 1, sitting right here, I would see network 10.1.2.0 down here as being a specific feasible distance away. So let's say it costs router 3 maybe a cost of 10, and we're talking about metrics right now, which we'll get deeper into with EIGRP. So we'll just say router 3 takes 10 to get there, and then it takes me maybe 600 to reach router 3. So the feasible distance for me to get to that network becomes 610. Just simple addition. The feasible distance plus the advertised distance. That's the second term. The advertised distance is how far away from your neighbor it is to reach that network. So in this case, that would be the cost of 10, feasible distance being the total cost of 610. So the reason we even bring these terms up, it seems like a pointless discussion until we hit this little note that I have down here in red. It says to be considered a feasible successor, the advertised distance must be less than the feasible distance of the successor. I'm not going to read that again because it's crazy if you read it without knowing what successor and feasible successor are. Successor, simply put, is the primary path. This is the one that ends up in your route table. So this is the best of the best paths. Now the feasible successor is the backup path. So let's say this way was a total feasible distance of 610, but this was, that 2400 baud WAN link, so it costs 1,000. Remember, lower costs are better to get there, and router 4 has the same fast Ethernet connection, so we'll say it's a cost of 10. Now, these numbers are totally out of my head. They do not match up to any EIGRP metric, just as an example. So the feasible distance to get there through router 4 would be 1,010. So obviously the successor or the primary path is going to be this way through router 3. It's got the best cost. Whereas the backup route or feasible successor is going to be through router 4. Now let's get back to the quote. It says, to be considered a feasible successor, the advertised distance must be less than the feasible distance of the successor. Now in this case, what that's saying is router 4's advertised distance, meaning the amount it takes for router 4 to get to the network, less than the feasible distance of the successor? So is 10 less than 610? Good grief, my horrible handwriting here. So let me back that out because that's pathetic. 10, is that less than 610? And the answer is absolutely, it is. So that will be considered a backup path that it's going to use. Now, you might be wondering why all this discussion, why is this in place? And I'm sure many questions are running through your mind because they're running through mine right now. First off, why is this rule in place? Isn't any path a good enough path? Well, the reason this rule is there is to prevent loops. And without getting too deep into the loop prevention, let's imagine that router 4 was not directly connected to that network. It didn't really have that fast Ethernet connection, but rather went through router 3 to get there. So from router 1's perspective, it's still seeing two paths. Router 3 saying, hey, I can get there. And router 4 is saying, well, I can get there too. It's still seeing two advertisements to get to the 10.1.2 network. But to keep loops from happening, what Cisco built in there was this rule to say, I'm not going to consider you a backup route if your advertised distance is not less than the feasible distance of the successor. Now realize that when router 4 advertises the route up, it will not be less than the feasible distance of the primary route if there was a loop in place. So that's all it is a loop prevention mechanism. But let's say that this was, this is our connection. We have this link right here, but router 4 had a really, really bad connection here. It was, a horrible token ring style connection. And so it's, it's a cost of $1,500 for router 4 to even reach that network itself. Well, the advertised distance is going to be 1,500 in that case, which is not, 1,500 is not less than the feasible distance of the successor, which is 610. So this will not be considered the backup route. Now, here's the question, and I'm sure this is the question that was running through my brain. So does that mean if this goes down, that router 1 will not use that as the backup path because it's too bad? Well, the answer to that is no. It will use it as a backup path. It's just going to take a little longer for it to find it. We're going to see the messages that EIGRP uses in just a second. And all that's going to happen is instead of having an instantaneous switch over to the backup route, it will have to send out query messages saying, hey, do you still have that path? Is that still around? To make sure that that's not a looped route or anything like that. And when router 4 responds and said, why, yes, I have that path, and it still costs this horrible amount, router 1's going to say, oh, okay, well, great. As long as you've got a path, it's better than mine because I don't have a path at all anymore, so I'll use you to get there. I don't want you to get too hung up on the rule and why it's there, other than to know that it is a loop prevention mechanism. But that is why we have to learn terms like feasible distance and advertised distance and successor and feasible successor. It's always been confusing to me because I always think successor. I always think of like successor to a throne or something like that would be the backup. But remember, successor is the primary. That is the king on the throne. The feasible successor, when you say it that way, that's like, oh, well, if the king dies, then someone will take over. That's the feasible successor. The last two terms that we're going to see is active route and passive route. Now, here's the funny thing. Again, a twist on words. Active routes are very bad. Passive routes are excellent. Here's the scoop. Let's say that, this one did cost 1500 and the primary went down. Well, router 1 immediately marks the route to 10.1.2 as an active route, as in it's actively trying to find a backup path to get there. We want to see passive routes because passive routes meaning everything's fine, it's just sitting there. Nothing bad is happening. That's a good route. These terms blew my mind until I actually saw them on a live router. Now, it just so happens that I've set up 4 routers, router 1, 2, 3, and 4, with this exact configuration. I've got WAN links between them. These exact networks are here. And I want to take us to a picture from router 1. Let me drag that over here to the screen and make it a wee bit bigger. Now, router 1, here we go, is right now sitting connected to everybody. I'm going to do a quick show IP route. And you can see that as of right now, it has 2 EIGRP learned route. That's the D, represents EIGRP, for the 10.1.1.0, which is the one over here on router 2. And it has the route for 10.1.2.0. Now notice just one path, it's actually going through router 4. In the live topology, I made router 4 being the more preferred route. We can actually switch these around. It's 1,000 over here and 600 over here. And so router 1 is saying router 4 is the preferred route, router 3 is my backup. But notice you don't see that here in the routing table. Here's where you get to see all of those terms in action. I think this is going to be a huge explanation. I'm going to type in show IP EIGRP topology. Now remember, that's one of the 3 tables, is the topology table. And right here we see all of the networks. Remember, the topology table is everything EIGRP knows about. Now you can see that I have 10.1.14, 13, and 12, which are actually the WAN links. I have the connection between 1 and 2 is 12, 1 and 4 is 14, and 1 and 3 is 13. So these are something EIGRP knows about. I have, you can see right here, 1 successor, meaning 1 primary route, and that's all we've got. And they're directly connected. You can see connected, connected. It's all right there. Now, what I want you to see and focus on is this route, 10.1.2.0. Notice 1 successors. So 1 primary path to get there, as you can see from the routing table. Now, unfortunately, it doesn't say 1 feasible successor, but instead, look closely here. It says, I've got 1 path via 10.1.14.2. That's the link right here between router 1 and router 4. So I'm saying I can get there for, on that path. I jump back here, and the cost is 236.5952. That's the feasible distance. Now right here is the advertised distance, by the way. So I see the feasible distance is this. Notice the feasible distance below here, 25.06752, not as good as this one. So obviously the WAN links are down, but notice the advertised distance is the same for this path. again representing that both of these have an Ethernet or fast Ethernet connection going here to the 10.1.2.0. So both routers are saying, hey, I can get there in the same amount. They're right next to me, but it all depends on how good the WAN link is from router 1 going down here to the network. So we see the two paths, but only one was chosen as the successor. Again, it doesn't show the feasible successor. Now, the last thing I'll show you right here is notice every single one of these routes. What are they marked as? P, which is passive. That's the good side. Active means it's down. We're actively trying to fail over or find some other network that can get us there. So that's kind of an action figure, if you will, for all of these terms, taking all of these terms into the live interface. Now, the last set of terms that we'll talk about deals with visiting the friendly EIGRP neighborhood, as in how do neighbors communicate. There are 5 messages that they use to communicate, and they speak via multicast. Now, if you haven't been too familiar with multicast, we actually have a whole section on multicast later on in this series. But multicast, I always compare it to like tuning into a radio frequency. Like you can see these two routers, if they're running EIGRP, they like tune in to the 224.0.0.10 frequency and use that frequency to speak to each other. You can almost think of it as like a duplicate IP address, and everybody has the same one and all use that frequency to communicate. So the first type of message that you'll see if you do a debug and you're trying to figure out what's going on is, of course, the hello message, excuse me. Now, these messages are the technical names. And the reason I want to say that is because we're going to do debugs when we get into the configuration, and you'll watch these go across. If you pull out Ethereal, a packet sniffer, and start capturing packets, you'll find out that Ethereal sees hello, update query. That's right in the header of this. So these are the technical terms, which when we get to OSPF, you're going to be like, man, I love EIGRP because there's so much madness on the conversation with OSPF. So first off, hello forms a relationship. They'll say, hello, hello, life is good, we're now neighbors. Once they do, they will start sending updates to each other saying, oh, by the way, I have this, I have that, and advertising the routes. The update protocol or the update language is what they use to send their routing tables to each other. Now, EIGRP is not like RIP in that it doesn't just broadcast the whole routing table on X number of seconds. EIGRP uses triggered updates, and it will only send partial updates of what needs to be sent. For example, if this router has a network and it goes down, it will send an update that just says that network's down rather than sending the whole routing table with that network missing like RIP does. Now, a query message comes across when a router is asking about a route, as if this network may have gone down and it wants to find out, does somebody have a backup path? It will send a query message saying, does anybody know about this? This router will get that and say, no, I don't. I don't have a backup path. And that's the reply. I've jumped ahead a message. A reply is just a response to a query. So it may say, yes, I do, or no, I don't. And that will be the answer to that question. Now, we're going to find out when we get into tuning EIGRP, these queries in a poorly designed network can tear you apart. If you have a huge network of, tons and tons of routers and you have not implemented it correctly with summarization in all the right areas, a query message will go out, go to this guy who will pass it to this guy and pass it to this guy, and that message will fly all around the network, hitting every single router, in a huge amount of depth. So one of the tuning points that we're going to look at with EIGRP is something known as bounding the queries, keeping them from going so far. Then finally is the acknowledgement. And this is just a built-in reliability mechanism. EIGRP does not run on top of TCP. It's its own layer 4 protocol. So it has to have acknowledgement. So when an update comes, it will say, got it. Here's my response. When a query comes, it says, got it. Now here's my response. Every single packet is acknowledged except a hello packet. And I guess, of course, an acknowledgement isn't acknowledged, or else you just end up in an endless loop. So all of the update, query, and replies will get an acknowledgement before they will get an answer. Now we come to the not so friendly neighborhood of the EIGRP metric calculation. I have a theory about this thing. EIGRP is a Cisco proprietary protocol. That is its real only weakness that it has, is only Cisco routers can run it. And my theory is that when the developers at Cisco created this routing protocol, they were thinking, well, this is a great routing protocol, but we don't want people to copy it. So let's see, how can we do that? Let's do this. Let's make the EIGRP metric so insanely sophisticated that nobody will be able to figure it out, including us. So they hired this, this guy up here. That's a picture of the guy who created this metric, and they said make this insanely complex for no reason. And he said, I will do that. And he goes and creates this formula that now nobody understands. It's not that bad, or as bad as it looks, I should say. Okay, I won't lie. It is as bad as it looks. It's a brutal formula, but the good news is you don't really have to know this. This is not going to be something you have to pull off the top of your head as you're configuring a router. And let's even back up a second. A metric. What is the metric? It's how a routing protocol figures out how good a route is. Like if we go back to our router right here, we have router 1, did a show IP route. Here's my two EIGRP routes. This first number is the administrative distance, or the believability of that. And the second number is the metric, meaning how good is that route in competition with other EIGRP routes. So if you heard about this metric, the EIGRP metric, from a CCNA series perspective, they would say, oh, well, that, that number is just a big number, and just remember that smaller is better. And that's about all you would know about the EIGRP metric. Now we're pulling back the mask of the number and going, there it is. That's the formula it uses to calculate it. Now the first thing is, Cisco Marketing says that the EIGRP metric is, number one, based off of the bandwidth and delay by default. The bandwidth being what number or what value did you type in under the interface using the bandwidth command, and you type that in. The delay of supposedly to be how long it takes the packet to get from one router to another. So if, for instance, a router had two paths like this, the theory goes that if this is maybe a T3 line and this is a T1 line, big difference there, the bandwidth would immediately say, well, use that one. But the delay is around that says if a packet, takes eons to get across that link, then maybe you want to prefer the T1 line, or the TT line, the T1 line, over the T3 because it has less delay. Now, that's what the marketing information will tell you. The truth of the matter is that both the bandwidth and the delay are statically configured values. And I've heard this misrepresented so many times. People think, oh, well, you type in the bandwidth, but it actually dynamically calculates the delay and finds out how long it takes the packet to get there. Fortunately, that's just not true. If you go under any interface and you type in show interface, we'll put serial 0. You will see under this interface the bandwidth right there, 1544 kilobits per second, and the delay. In this case, 20,000 microseconds. That's what USEC is. Now, if I were to go over to another router, let me hop over to, router 2 here. And I'm going to type in show interface serial 0. I'm looking. I see, oh, well, that's funny. Bandwidth, 1544, exactly as it was before. And delay, 20,000 microseconds. Well, that's odd, if it's in the terms of microseconds. Remember, microseconds is even smaller than a millisecond. So you'd think there'd be some difference, and there's not, ever. Because you can go under the interface, and we know how to configure the bandwidth, right? We just type in bandwidth and a value. But not many people know this. You can also type in delay and a value there. Look at that. So both of those are statically configured values, and those two values is what the Cisco router uses by default. Now, with that in mind, you can turn on any one of these other three metrics, the reliability, the load, or the MTU. Now, Cisco says that in their marketing material, and you'll see it plastered all over EIGRP, and they'll say, this is great. We have a the best metric in the world. But then if you go to find how to turn those on, they will say, well, why do you want to do it? And you actually have to call TAC. You won't find it on their website. The commands used to turn those on, because Cisco recommends you never turn them on. The reason why is because these are all dynamic values, meaning they can change on the fly, with, would say, with the exception of the maximum transmission unit, or how big a packet is. Those are statically configured on the interface. But reliability and load, those change all the time. For example, take the load. Somebody opens a web browser and surfs the net at your corporation, the load goes up. They close the web browser, the load goes down. So the load is always going up and down. And you know what happens if you choose to include the load in the EIGRP metric? Well, every single time the load increases on that T1 line, somebody surfs the web, EIGRP is like, oh, load change, recalculate. And it runs the dual algorithm to say, oh, is there a new route now that the load has changed? Oh, no, okay. Somebody closes the web browser, it's like, oh, load change, rerun the calculation. And it goes around, tries to rerun the calculation. So this, if you include these things, your processor gets pegged because the algorithm keeps running all the time for no apparent reason. So this mother of all formula right here that you see is the formula that's used if you choose to include all 5 metrics into your calculation. All 5 of those metrics will plug all the individual numbers inside of there, the reliability, the load, all of that, into this formula and spit out a number. And that number will be what you see right, well, not right there. How about right here? When you do a show IP route, that will be the value that you can see right here. Now, with that in mind, nobody turns on those other 3 values. Or I should say, I have never encountered somebody that does. So to boil it real simple, or as simple as this metric can get, the real metric by default, just using bandwidth and delay, is just 256 times bandwidth plus delay. But remember, they hired the guy in the corner to say, make this extremely difficult for no reason. So the real values for bandwidth and delay is this. They said the bandwidth is really going to be 10 to the power of 7 divided by the bandwidth in kilobits per second. So if your bandwidth is 128K, really it's going to be 10 to the power of 7 divided by 128K, and that value will go right there. The delay is in microseconds, or I should say, sorry, in tens of microseconds. See, I can't believe I typed that. This is says to microseconds, but put tens right there. Tens of microseconds is what the delay is. So, for instance, when you look on the show interface command, like we saw, let me just scroll back up right here. When you say delay 20,000 USEC, that's microseconds, the delay value that they really plug in there is microseconds divided by 10. So that will be plugged in the delay, multiply that by 256, and that is how you get this value right there in the show IP route command. Now, again, that's one of those things that's probably valuable on Who Wants to Be a Millionaire, on the $1,000 million question, but not going to be something that you use typically in the real world unless a metric is really coming out wrong and you're trying to figure out why is it coming out as so. Now, I know some of you are preparing for the certification exam, and I also want to make sure that you know that these formulas are not going to be, you're not going to have to fill in the blanks on the certification exam. You won't have to know these formulas to figure out a metric. But what you will want to know is that these things are known as K values. All of these criteria are known as the different K values for EIGRP. And in order for the neighbors to form, so if I have a neighbor up here speaking to a neighbor down here, they have to be using the same K values. So here's a troubleshooting step. A hello message, you're checking in the debug, comes across and goes to this router, and it's so rude. It never sends back a response. It just says, you know what, I'm ignoring you. A lot of times that will be because there is a K value mismatch. For example, the administrator on this router may have chose to include the load in its calculations, and this administrator didn't. So at that point, the neighbor relationship is severed because they're using different formulas to calculate their metrics. With that in place, let's go ahead and draw the line on the concepts of EIGRP and get moving into the configuration. To wrap up the high points, we talked about Why we would choose EIGRP? Number one reason I would still say is because it uses the backup routes, but we had a whole list of reasons of why we would do that. The big part was going through the tables and the terminology. The three tables, the route table, the topology table, and the neighbor table all go together into one EIGRP process, and then knowing the terms is the other half of the battle. Knowing what a successor, feasible successor, uh, the terms, all the ones we talked about, the advertised distance, the feasible distance, all of those terms melting together. We then looked at visiting the friendly EIGRP neighborhood, and the point of that was that there's very little for neighbors to actually form. Just so that list of messages, the hellos, the updates, the queries, replies, acknowledgments, 5 messages that they use to speak to each other. And those are simple to find in debugs and packet sniffers. Now, when it comes to OSPF, you're going to find the neighborhood is not very friendly. You're going to have a huge amount of messages and types of messages that can be exchanged, and the process is immensely more complex. The only thing that's complex in the EIGRP world is that metric, which you will never have to see again, I promise. That not so friendly metric is how it generates those massive values that you see in the routing table for it to find the best route. I hope this has been informative for you, and I'd like to thank you for viewing.